Now, how many words in this paragraph? The James Webb Space Telescope has done what many thought impossible. It has found a galaxy so distant, so ancient, and so perplexing that its discovery might force us to fundamentally rewrite everything we thought we knew about the early universe. It challenges the very foundation of our cosmological understanding and beckons us to reconsider the models that have shaped decades of scientific consensus. But to grasp why this revelation is so monumental, we must first rewind, though not all the way back to the Big Bang, but to the relatively recent year of 2022. Until that point, the Hubble Space Telescope held the record for identifying the farthest galaxy ever seen, JWST, a glowing ember from the cosmos' infancy, a relic of light from when the universe was still young. It served as a time capsule, offering humanity one of its first glimpses into the dawn of galaxies. However, Hubble, despite its groundbreaking contributions, had limitations. Its 2.4-meter mirror, though powerful, could only look so far into the depths of cosmic history. Its reach was constrained, its clarity limited, especially when observing in the infrared spectrum. That's where JWST came in. With its vast 6.5-meter golden mirror, precisely engineered and finely tuned to detect infrared wavelengths, the telescope was perfectly suited for capturing the universe's most ancient light stretched and redshifted over billions of years. This wasn't just an upgrade, it was a revolution. JWST didn't merely surpass Hubble's legacy, it obliterated it, redefined it, and shattered our previous boundaries of exploration. Early in its mission, JWST spotted a galaxy known as Z140, exhibiting a redshift of 14.32, a staggering number that placed it far earlier in the universe's timeline than Z11. At the time, that discovery alone was a breakthrough. But what came next redefined the limits of what astronomers thought was possible. A subsequent detection uncovered an even more distant galaxy, nicknamed MOM, Z14, with a redshift of 14.44, nudging our observational window closer to the very birth of the cosmos. But it wasn't just the redshift or the age of the galaxy that stunned scientists. It was what this galaxy actually was that provoked such awe. MOM, Z14 is incredibly small, only about 500 light-years across. To put that into perspective, our own Milky Way galaxy spans over 100,000 light-years. This distant galaxy is a speck by comparison, barely a whisper on the cosmic scale. And yet, it shines with extraordinary brilliance. It's undergoing a star formation frenzy, an intense, almost chaotic period of stellar birth that's far beyond what scientists believed was possible at such an early point in the universe's history. This furious activity contradicts long-held assumptions. In the earliest epochs, galaxies were presumed to be dim, primitive, slowly evolving systems composed mostly of hydrogen and helium. But MOM, Z14 doesn't fit that mold. It's bursting with energy, forming stars rapidly and abundantly, throwing a wrench into our expectations. Even more puzzling is what's missing. Every major galaxy we've studied, including our own, is anchored by a supermassive black hole at its core, a gravitational behemoth that influences everything from star formation to galactic structure. But in this infant galaxy, there appears to be no such anchor. No supermassive black hole. Just newborn stars and eerie silence. The absence of this gravitational center is not only unusual, it's unprecedented. And the oddities don't stop there. When astronomers analyzed the spectroscopic data from MOM, Z14, they found something even more baffling: nitrogen. And not just random traces of it, but a distinct chemical signature that mirrors the composition of some of the oldest globular clusters orbiting the Milky Way. This raises an important implication. MOM, Z14 is not a pristine, first-generation galaxy. It's been enriched. That means stars have already come and gone before it. They've lived, gone supernova, and seeded the surrounding space with heavier elements. In other words, this galaxy is the product of a second, or perhaps even third generation of cosmic evolution. That changes everything. It implies that galaxies began assembling and enriching themselves far earlier than our models have ever predicted. If star formation and stellar death were already well underway by the time of MOM, Z14's existence, then the universe was maturing at an alarmingly rapid pace, assembling complexity in a fraction of the time we thought necessary. Our existing cosmological models have always painted a picture of the early universe as a quiet, dim, chemically simple place. Mom, Z14 completely shatters that image. And the more the JWST looks, the more it finds similar anomalies, bright red galaxies scattered like ancient beacons across the sky. These galaxies don't just defy our expectations. They challenge the entire map of cosmic history. Each discovery reinforces a disquieting question. Are our models fundamentally flawed? Not necessarily incorrect in entirety, but perhaps incomplete, missing vital components that are now coming to light. And just when it feels like things couldn't get stranger, they do. Some scientists have taken these anomalies as potential evidence for a truly radical theory. What if our entire universe exists inside a black hole? It sounds like science fiction, but there's a compelling logic behind it. When a black hole forms, it creates an event horizon, a boundary beyond which nothing escapes. According to theory, everything that crosses this threshold becomes isolated from the rest of the universe. But what if that isolation isn't the end? What if, within that boundary, a new universe begins? This idea forms the basis of black hole cosmology. The theory suggests that the Big Bang wasn't an explosion within empty space, but rather the collapse of matter into a black hole within a larger, parent universe. The singularity at the core of the black hole becomes the seed, and the moment of collapse becomes the birth of time and space as we understand them. Imagine that. Every black hole could be a portal to a new universe. Perhaps our own cosmos is one of many, born in the heart of another universe, branching out like a cosmic tree. This could also help explain the uncanny fine-tuning of our universe, the seemingly perfect balance of forces and constants that allow life to exist. Maybe only universes that emerge from stable black holes can support life, perhaps those that don't simply fade away. In this view, we are the survivors of cosmic natural selection, and the mysteries only deepen. Researchers examining the spin of galaxies have noticed a strange imbalance. An overwhelming majority spin in the same direction. In a truly random universe, you'd expect a roughly even distribution. This odd symmetry hints at something deeper, a hidden structure, maybe even a preferred direction or axis embedded in the cosmos itself. If true, this would upend the long-held cosmological principle that the universe looks the same in every direction. This axis could be a lingering fingerprint from the parent black hole that birthed our cosmos, an echo of its collapse and expansion. And the plot thickens further. In advanced versions of Einstein's general theory of relativity, space-time doesn't just bend, it can twist. This property, known as torsion, could act as a repulsive force under extreme conditions, preventing the formation of a true singularity. Instead of collapsing to an infinite point, the core of a black hole might rebound, expanding outward and giving rise to a new universe in the process. And that, perhaps, is what we call the Big Bang. Not the beginning of everything, but the continuation of a process as old as reality itself. This changes our cosmic perspective. The universe is no longer a singular event, it's a chain reaction. Universes give rise to black holes, which in turn create more universes, repeating in a potentially infinite loop. And it's not just theoretical. Observations from deep field surveys are turning up massive, mature galaxies just a few 100 million years after the supposed beginning of time. Galaxies far too evolved for how young the universe should have been. These findings don't merely adjust our cosmic timeline. They destabilize its foundations. Maybe, just maybe, we haven't miscalculated. Maybe the universe is simply far stranger, more layered, and more intricate than we ever dared to dream. The James Webb Space Telescope has flung open a window, not just into the early universe, but into the very fabric of reality. In this new view, galaxies like Mom, Z14 aren't rare anomalies. They may be the norm. The Big Bang may not be the genesis, but one moment in a much longer story. And each discovery leads to new questions, deeper mysteries, and the possibility that we are only beginning to understand the true nature of existence. This is the new frontier, not just of space, but of thought. And that is where the Rayall journey begins. As we dig deeper into the implications of these early galaxies, a larger and more philosophical question begins to take shape. What else might we be missing about the nature of the cosmos? If our models of galactic evolution can be so thoroughly overturned by a single telescope's first glimpses, what does that say about the broader structure of the universe, or the assumptions that underlie much of modern cosmology? The James Webb Space Telescope has done more than just capture images of ancient light. It has opened the door to a realm of questions that span beyond astrophysics and reach into the very nature of existence. For instance, if galaxies like MOM, Z14-formed stars, enriched their environments, and hosted complex chemical processes in a universe that was supposedly still in its infancy, then the timeline for cosmic development must be dramatically compressed. But how is that possible without fundamentally revising our understanding of matter distribution, gravitational collapse, and the influence of dark matter in the early universe? The mystery deepens when we consider the role of dark matter itself. This invisible, enigmatic substance is believed to make up roughly 27% of the universe, yet we cannot see or directly detect it. Its presence is inferred only through its gravitational effects, especially on the rotation of galaxies and the formation of large-scale cosmic structures. Could it be that dark matter played an even more significant role in the accelerated formation of galaxies than previously thought? Perhaps dense clumps of dark matter served as gravitational wells, rapidly pulling in gas and dust to seed the birth of these early, luminous galaxies. If so, that would suggest that dark matter is not just a passive participant in the cosmic story, but an active sculptor of the universe's early framework. Another layer to this emerging picture involves dark energy, the mysterious force driving the accelerating expansion of the universe. While it remains largely theoretical and poorly understood, dark energy makes up an estimated 68% of the cosmos. If dark energy's influence was somehow different in the early universe, or if it interacted with matter in a way we haven't yet uncovered, it might help explain the existence of these dense, active galaxies. Could the balance between dark matter and dark energy have been different billions of years ago, tilting in a way that allowed structure to emerge more quickly? These are the kinds of questions now being asked in research labs and observatories across the globe, all triggered by the unexpected findings from a telescope launched just a few years ago. Moreover, the philosophical ramifications are just as profound. The idea that we might be living in a universe born from the collapse of a black hole suggests that our cosmos has a lineage, a parent reality from which it sprang. This raises questions not just about origins, but about the future. If our universe was born from a black hole, could it someday collapse and give rise to another? What would that universe look like? Would the laws of physics be similar? Would time flow in the same direction? Would life